I see it's exactly 7:30. John, would you like to introduce tonight's speaker?
Yeah, let me introduce Jeff Schockler, who is going to introduce tonight's speaker. Jeff, take it away.
Thank you, John. And Maddie, I am incredibly jealous and I wish I could be an IceCube intern. So congratulations on that. That's just phenomenal. It is my great pleasure to introduce Steve today. Steve Barnett and I have known each other now since 2017, actually. He and I did a Big Ten IT leadership professional development program that lasted 9 months together. Got to know each other really well, didn't know each other before that. And as soon as he opened his mouth, I think on the first day of our experience and said he worked with IceCube, you can imagine how I responded to that. And he was shocked that I knew what IceCube was. And the relationship has gone on from there. Steve Barnett has a background in computer science. He's been with the University of Wisconsin-Madison since the mid-90s and worked for a number of research groups there, doing computer and IT related support of research at the institution. And he also happens to be the guy with the data and the computer infrastructure support for the IceCube Neutrino Telescope at the South Pole. And I'm sure he'll be sharing with you the fact that he has been to the South Pole, which is also incredibly awesome, and I'm seethingly jealous about. But I'm very much looking forward to his talk today, where he's going to kind of give us a behind the scenes look at what it takes to kind of make a global scale, large scale, multi-year, decadal research project in astronomy and astrophysics work. So it's my great pleasure to introduce Steve Barnett tonight. Steve?
Wow, thank you. Well, thank you all for having me. Jeff, thanks for the great introduction, and thanks to both Jeff and John for putting up with me as we got ready to do this. As you get busy, and they kept like, hey, throw us a bone here, throw us a bone. So they did a great job of herding this particular cat, made it really easy to come and do that. And it is a pleasure to join you all tonight. It's nice. I see a couple of familiar names and faces in the room from floating around from UW. So that is always pleasant. And so with that, I guess I will get things started here. I will share the screen and away we'll go. Okay. All right, can everybody see me okay? All right.
Looks good, Steve.
Excellent. Okay, so as Jeff said, my name is Steve Barnett, and I work at IceCube, which is absolutely a spectacular gig to work at. I come from northern Wisconsin. I've lived in Wisconsin pretty much all of my life, and grew up in rural northern Wisconsin, up in the Phillips Park Falls, Ladysmith area. So if you hold up your hand and point, it's kind of right in the middle of everything that you might know about the Wausau's, Eau Claire's, Green Bay's, Superior, some of the bigger locales in Wisconsin. It's kind of smack dab in the middle of them. So right in the woods. I moved down here to follow my wife. She was pursuing a master's degree in statistics, and I thought that it was probably best to follow her along as she did that. And that got me tied into the university, where, as Jeff said, I bounced around to a few different places. Started off at the Space Science and Engineering Center. Really cool place to work. Lots of satellite dishes floating around out there. Amazing history. The place that actually was instrumental in developing the first weather satellites. So just incredible. From there, did a brief stint in industry at Burby here in town, and as a result of that, discovered that there's just a lot of good stuff going on in the research and academic world that you just don't get in the private sector necessarily. So bounced back to the university to work in the chemistry department, worked there for about 4 years or so, and then through a contact, got the call from IceCube to say, hey, would you like to come work on computing with us? And that's the sort of thing. I mean, it was sort of a tough choice at some level. The chemistry department is a very nice place to work. But when you get the kind of the call to do some of the big science stuff, it's hard to turn down an opportunity like that. So that was circa 2005, right as construction of the instrument was beginning. It was a very exciting time, a lot to learn, a lot to pick up, and it's kind of kept going from there. So full disclosure, I am not a domain scientist. My knowledge of astrophysics is purely what I can pick up through osmosis, through working with people who do this every day. It's amazing, the things I've learned and the things I have yet to learn. It's absolutely breathtaking. Having said that, I've been at the Cube for 15 years, so I have picked up a trick or two. I have been down to the South Pole twice. It lives up to its billing. It is cold, it is dry, but it's absolutely the experience of a lifetime, to do that. So I feel very privileged to have been able to do that. It was one of those things as you think of as a kid, that, hey, I'd like to, you see all the cool things and you want to do those science things. And then one day you wake up and realized you just did it. And it's kind of weird because on the one hand, it's like, this is amazing. I've kind of gotten where I was thinking I was going, but it still feels like a job, and just that's what we do. So it's been an interesting road to get here. So having said all of that for the presentation tonight, I understand that it's fairly common to, kind of hold question toward the end, but if at any point there are questions, that you want to jump in, please feel free. A lot of these, I like to do these talks when they're in person, it's much easier to make them dynamic and to be able to sit down and really take the conversation, in different directions. A little harder to do virtual, but but honestly, if something grabs your attention, more than happy to sit down and follow that where it goes. So, please keep me posted. All right, and I understand that Francis has spoken before. He's obviously the guy who conceived of the whole experiment way back when. So, he can talk about the lofty science goals and the and really vision for the future sort of thing. My part of the puzzle is much more the mundane kind of nuts and bolts, heavy lifting that has to go on to try to take that vision and get as close to it as we possibly can. And it's been an absolute blast working on that. A lot of blood, sweat, and tears have gone into this project from myself and a few thousand people around the world. So on that note then, let's get rolling. So we'll go a little bit through IceCube for those of you who might not have heard Francis talk, or just a little bit of background to level set. IceCube itself, I think of it as a scientific collaboration. It is about 400 people at any given time. Those are faculty members at research institutions around the world, institutions of higher ed, at government labs. We got a few DOE labs in the mix. It's mostly NSF funded, although we do have international funding as well. Currently, there are 56 institutions around the world. And we try to glue all of those people together, over time. And so that's kind of IceCube in a nutshell, is basically a lot of people trying to get some interesting astrophysics research done, push back some boundaries. The detector itself, when we get to it, is a neutrino detector. Those are the particles we're most interested in. There's lots of fun stuff, other things besides neutrinos, obviously, floating through the detector. Lots of muons and cosmic ray particles that are, able to travel even to the depth in the ice that we've buried the detector. But the ones that we're really interested in are those neutrinos. It's situated down at the geographic South Pole, which has a whole slew of challenges in working with, but has a lot of interesting benefits there as well. Um, so, a little bit without going too much into it. I won't fully read this here. But the upshot of this information, looking at this, is that we don't actually directly detect neutrinos. Neutrinos interact with something else. In this case, we have ice, and they produce a secondary particle called a muon that goes hopefully shooting through our detector and producing light. And it's actually that light that we detect and follow along. And that is kind of the reason for doing the South Pole, right? So the first experiments, they posited the neutrino and its existence in the 1930s, they said, but the problem was that trying to detect it was really a mystery for them at the time. And it took a long time before they could even start to, prove that the thing actually existed, that it wasn't just an artifact of the mathematics and the model that they were using. So in those cases, and in a lot of cases still, they use tanks of water to act as the interaction medium. That's great, for detecting these things at some scale. But the problem is that the way you can characterize the neutrino, its energy, its direction, and those sorts of things, you need a fairly large volume. The other thing is, given that they don't interact very often, the number of particles that you're going to see in a year is a function of the size or the volume of the detection medium that you're in. So what you want to try to do is get as big as you can and as dark as you can. Now the trick is that you can build giant tanks of water, but that's extremely expensive. So they got the idea, Francis Halzen actually, and a couple of his contemporaries had the idea of saying, hey, what if we could use ice as the detection medium? And they actually did a prototype, kind of a proof of concept, where they drilled a hole in the ice sheet in Greenland and lowered a single photomultiplier tube down into that hole. And it actually worked the way they expected. And that gave them the idea and the confidence to say, we could actually build this at a large enough scale to detect interesting things in the universe. And so that kind of got the whole thing rolling. The nice thing is that the ice down at the South Pole is very, very clear. It's 2.5 kilometers deep. So it's a very large amount of ice. It's moving. It is a glacier, so that makes things a little bit interesting. Fortunately, it hasn't had any particular impact on the detector as far as we can tell. But it is at those depths extremely clear. I think they've said they figure that photons can travel up to 600 meters through ice. It is that transparent. And of course, given that it's buried at a depth from 1.5 kilometers down to 2.5, that means that there's a significant volume of ice above it, which reduces the background of particles coming in. It doesn't eliminate them by any means, but it certainly does reduce it to make the problem of pulling the neutrinos out of the background a much more tractable problem. All right, so so there it is. It gives some basic stats about the detector itself. As I say, it took 5 years to build it, basically running through the austral summer of the South Pole. That adds lots of interesting logistical difficulties. You have to be kind of ready to go. It's an interesting problem. For those of you who have been in academia, there's sort of a, it's a fluid pace, right? At times it moves really quickly when you're trying to get, some results out the door and things like that. But other times when you're trying to dig through, complicated problems, it can take a while and things kind of come at a different pace. When you're doing the construction work, it's very much an execution thing, right? We need to get things in, they need to get here on time. If they're not ready to ship on this date, they don't ship until next year. So, keep moving, move fast, hit the deadlines and keep going, which is really an interesting thing. The cadence was kind of, go down, operate during the season, you get back in January, February, as people are trickling back from the Southern Hemisphere. You sit down, you start planning what you're going to do for the next season, you buy what you're going to buy so that it shows up by, late spring, early summer. test it out, burn it in, make sure that it's all going to work. And then starting in September, you pack it up, get it into the cargo chain. November, you follow it down, do the, whatever you got scheduled for the season. We would deploy, additional computers to support new strings as they were being drilled into the ice. Get that going, and then, wrap that up and then do it again. And it just one after the other. It was exhausting, but it was a wild ride. Always, crazy things going on, never a dull moment, as much as sometimes even you might want one. So that was kind of getting it rolling. This is a picture of the drilling site, or a drilling site. So this is one hole being drilled here. If you take a look at the back here, the thing that looks like a big, fishing reel, essentially that's what it is, but that's a reel capable of holding a 2.5 kilometer length of hose. So the holes are drilled with hot water. Essentially it's a giant car wash. Basically, you just sit down and you inject near boiling water into the hole, and you just let the thing sink to the depth of 2.5 kilometers. That takes anywhere from 28 to 36 hours. And then you pull the hose out and you lower the detectors in. So this is one of our optical modules being lowered down into the ice. It takes about 14 to 18 hours to actually connect all of the optical modules, give them their final test to make sure that the connection is good and that the electronics are working, and then lower it to the next station and just keep attaching the DOMs, the optical modules. And once the drilling activities themselves start, that's a 24/7 operation down at the poles. So those folks were, basically 3 shifts, and you just, churn, and chug through that. So that's all great, but I mean, we're here to talk about data and stuff, right? I mean, what do we got going on here? So the interesting aspect, and the things that are most interesting probably for folks interested in astronomy, what are the astrophysical, what are we looking at here? What are the applications in astronomy? A lot of the initial work was kind of particle physics work, right? Trying to characterize and understand neutrinos a little bit better. Honestly, early on, just getting used to how the detector itself behaves, what its systematic errors might be, and all of those sorts of good things, and getting that going. But the interesting thing about neutrinos is that they don't interact with electromagnetic fields. And what that means is that unlike most other particles, you don't lose directional information, right? So the cosmic rays that are bombarding us all the time, have been tumbled through all of the magnetic fields, locally in the atmosphere, but also, anything that happened to be in the way. And so you don't know for sure what the actual source of the neutrino, or what the actual source of the particle is. With neutrinos, they point back exactly to the source that created them. So that makes them somewhat interesting if you can make the track accurate enough. And as we'll see later, that gets to be a bit of a trick. So as you get this thing drilled in and you've done the commissioning and all that sort of good work, then you start the data taking, and that's what we're doing now. What we've been doing basically since completion in 2010 has pretty much been doing that. The instrument itself produces about 1 terabyte per day of raw data. At the time, if you go back to 2010, that was a huge amount of data. These days, when I'm talking to people around campus doing different things, you talk to folks who are, working in, biochem labs where they're doing imaging with microscopes, and they're, taking 50 images at a time, but like, incredibly short time scales, and then, 4K high def images, and, they're cranking out 30 to 40 terabytes in one data set. It's pretty impressive when you look at that sort of thing. The only thing that we've got in some cases that they don't have in those places, that for us is a 24/7 thing. So, we're constantly, staring at that ice, and about 1 terabyte a day. And over a year, that piles up to, 370 or so terabytes when you include some of the auxiliary data that comes along with it. So we have to catch that and then manage it. but more importantly is try to dig the signals out of that. There's a few neutrino candidates a day, generally speaking, for an instrument this size. But the trick is to decide, okay, did we see an actual neutrino or just something that kind of looked like it, given the amount of particles flowing through the detector at that time. Sometimes it's easy. If we get a particle traveling upward through the detector, so in other words, that it came from the northern hemisphere through the Earth, the only particle that can do that is the neutrino. Everything else is absorbed well before that. So those are easy. If we see one going up, we got one. That's easy. The tricky part, and where they've spent a lot of effort, is trying to increase the sensitivity of the instrument to other parts of the sky, right? So detecting from the southern hemisphere is particularly difficult because of the background of cosmic rays and then even atmospheric neutrinos locally. So that's our job, is to kind of sort through that soup and find the interesting things in there. Now, the nice thing is that most of the people are interested in the neutrinos and those particles, but there are plenty of other folks who are actually interested in what we call the noise, right? There's interesting things to find out in there. Some of the folks studying cosmic rays, for example, have detected an isotropy. So essentially, we have more cosmic rays coming from one part of the sky than the other. And the hypothesis at one point was that that should look more or less uniform, but it turns out it doesn't. And we were kind of one of the first places to find that out, or be able to really definitively say that. So there's interesting things even outside the original intent of and design of the instrument. So then what that translates to for us, one of the interesting aspects are things that we're calling multi-messenger astronomy. And so, if we look at this slide, the 10,000-foot view, up in the right corner there, we see interesting things and objects in the sky that might produce neutrinos, that we think should produce neutrinos, at least according to all the math that we have. The tricky part then is, can we find them and can we point to them? And so the idea then is that one of these things comes shooting through our detector. We find it, we send at least an alert or a notification to other facilities to let them know that we've detected something interesting and it's roughly in this part of the sky. And so there's, as you can see there, the observatories in different parts of the spectrum. One of the interesting ones is LIGO. That one, they don't really sit down and see things directionally, as far as I understand, or at least not yet. Some of their enhancements might give them better directional information as they build out more of those facilities. But they can go back and look through their data set and see if they detect any interesting events coincident, with one of ours. So, that is still very much work in progress at this point. That's, one of our very active areas of research, is taking all of these various instruments and trying to help them work together more effectively, hopefully to see. Yes?
Are these alerts generated at the South Pole, or are they done through Madison?
They're generated at the South Pole. So what happens is, down there we sit down and we have to do a bunch of very quick first cuts on the data, just to look and say, okay, is this interesting? When we find an event that is interesting, we take just that event, and an event itself for us individually is very small. It's a few tens of kilobytes, maybe. It's not a big chunk of data that we have to throw around. So we can actually shoot that over Iridium satellites. We can actually get that transferred pretty much 24/7. So as soon as we detect that, we say, okay, we detected it, and this is what we think it is right now. Now, the trick is, right at that point, there's still a pretty significant error. The analyses that they've done online at the pole have to be done very quickly, because we're seeing about 3,000 particles a second flying through the detector, or 3,000 tracks going through the detector per second. So, getting very, very high degrees of accuracy, and high here isn't really that high in astronomical terms. I think we're shooting for sub-degree accuracy at this point. So, a degree one way or the other is a pretty huge chunk of sky, especially if you're trying to convince somebody that they should point to, very expensive instrument based on that. So, but we do send that up. So that first cut is pretty crude. And then up here, we do further analysis to sit down and say, okay, now we do the heavy computational lifting. And, that processing takes, a few thousand CPUs, and we grind for about an hour to sit down and kind of look and say, okay, yes, we think we got, something real. Or in a lot of cases, hey, you know what, it looked good at first blush, but it's, it didn't pan out. So, so that comes up live from the poll. Yeah, great question. Thank you. All right. So that's the nice, happy idea. But as you might guess, it gets a little more complicated. So, now we start breaking it down into some of the more details. The interesting aspects that we run into that have some of the biggest impact on the way we have to operate is if you look at this line in the middle here, that's kind of the north-south line, and it's telling you how our data gets north. And essentially that is, for the most part, it's done via satellite on a daily basis. And then via ship in other cases. So what you'll see here is we have two satellite families. So the Iridium satellites, most of you are probably familiar with theirs. They're low bandwidth communication satellites. And they're pretty good for small amounts of data in small bursts. They work well for that. In some of the modes, you can get remote network access that way, but I mean, it's like the good old 300 baud modem days for those of you who remember those. If you don't remember those, you should count yourself lucky. It was very slow typing is the best way to describe that. But it gets you access at least to the facility, so you can do some basic things kind of 24/7. The bulk data, so most of the data as we sit down and collect that and we squirt back daily, comes in over the TDRA satellites. And those are NASA operated satellites that do mission support for all of the various NASA missions. But when they don't, when they have available time slots on there, NSF pays them to shuttle our data north. And using those, we can get about 100 gigabytes per day transferred from the station back here up to UW-Madison. And obviously that's about 1/10 of what we actually take in. So our data gets written on the station. We write 2 copies of the data to separate sets of hard drives at this point. And then put those on the shelf until the station opens up, and then we ship those back north, literally via ship every year. And they arrive usually about in the spring. All of this data lands, kind of starts its science journey here at the data warehouse at UW. But from there, it enjoys a wide ranging life. We, our various collaborators at the institutions around the world will copy some of that locally if they're going to be working on it. A lot of times they can get more, down in depth with the pieces of it that they have if they're working with local resources. So they will, pull parts of interest back to them and work with it locally. We have to archive that data so that we can preserve it. So, from there we sit down and say, okay, which parts get transferred, and we've got whole piles of software to deal with that particular data flow to make sure that we keep it safe. And then, there's just all of the analysis work that needs to go on. A lot of that happens locally here, but there's big chunks of it that actually get farmed out to facilities all around the world to get the analyses done. So I don't know, are there any?
Steve, I have a question. So the 100
Yeah.
gigabytes worth of bandwidth that you have daily that can go via TDRS,
Yep.
that must be the stuff that kind of gets flagged as priority or candidate kind of material. So there's a prioritization schema that's being applied that says, all right, this goes into the satellite feed, this goes on the slow boat north.
Yep. Yes.
Yeah.
Yep. Yeah, absolutely. So there's, it's actually, there's probably 3 or 4, priority tiers. So one of them is the, hey, this looks like an astrophysical event, right? So a neutrino that was sourced not from the sun or the atmosphere. So something that is non-local, and that's the stuff that we're, everybody's super jazzed about that stuff, right? That's pointing to interesting things in the sky. And that gets shot over right away. There's secondary streams that come over that as well that are, low level kind of monitoring health data, right? Everything is working correctly. Okay. And then yes, the slow boat stuff, or the TDRS satellite stuff that comes over in bulk, that's the reduced volume. So we'll see here in a second kind of a picture of the farm, the computing farm that does that on station to decide what's interesting and what's not, and what makes it into there, and does a lot of the compression to try to make it so that we get as much as possible over that link. So that is a great segue to look and say, okay, our processing starts right here. So what you're looking at, we had our little building up on the top of the detector. All of the red cables that you see are actually the surface cables that come from the downhole detector. So each optical module, basically each cable that you see in there, is connected to an optical module 2.5 kilometers deep in the ice, or thereabouts. So as such, that's an awful lot of cable. It's hard to convey in this picture exactly how much cable that is. I can tell you that those cables are heavy. So when they sit down, they drill the holes, they run the cables down in there, and then at some point you have to snake the cable up into the building, and that is a process. Actually, it took about 12 people to horse the cables in there. They had tried to come up with a mechanical method for being able to do this, but it's an interesting thing. A lot of times people look and they say, hey, you must have a lot of really high-tech stuff to work in this environment. But the problem with high-tech stuff is it breaks in ways that are really hard to fix. Okay, so a lot of this stuff is actually more do-it-yourself sort of things. And so they had tried to come up with some mechanical means of doing this, and it turned out at the end of the day that if you just got a dozen people and you grabbed on the cable and you pushed it up the pipe and pulled it through, that was about as good as it was going to get. I mean, we pulled up, I think, 7 to 10 cables a day you could do that way before people said, okay, we've had enough, because they are heavy. So, all right. And so all of those, we think, if we look at this, what we want to think of when we see a particle is something that looks like this, right? So this is a simulation produced. This is a muon flying through the detector, producing all sorts of interesting little secondary particles as it interacts going through. And that's the nice, clean, pretty picture, right? This is a particle. This is a track, okay? Great. That is wonderful. The trick is that if we look at this, what we're about to see represents 10 milliseconds of what the data looks like to the detector itself. So what we're going to see here are the strings lowered down into the ice, and then as the light reaches the detector and they start activating, you're going to see them turn on, right? And so what we try to do as they're turning on, if we look here, you see these lines, this is the guesstimated track of the particles coming through here. So if we watch this, and you just sit down and you look at that, at the end of 10 milliseconds, pretty much everything has been lit up, right? So the trick then is to sit down and look at this and say, wait a minute, as these things are lighting up and as light is hitting this, right? We're looking at 10 milliseconds worth of time. So 100 times a second, it's going to have to sort through this mess and figure out which of these things are particles. And if they are, what was the actual track of that particle through there? To say that that's a difficult problem is understating it. There are a large number of PhDs that were granted exactly for solving that sort of problem. But they did it, amazingly enough. It's absolutely incredible to me that they were able to sit down and take something that looks like that and say, no, we know where the, things are going through. So that is the beginning, is that that processing farm that you see down there. So first of it is reading out all of the data from those detectors. And that's really the only custom piece of hardware that we use, is to just simply sit down, connect to those cables, and then handle the signaling that come out of them. The rest of it then starts off with single board computers that kind of bunch up, so take all of the collected data from that, package it up, and then they hand it to commodity computers. There are about, what it's difficult to see in that picture, there are about 50 or 55 normal computers. Currently, we buy them from Dell. That sit down, and those things have the job of basically doing the quick guesses as to what the tracks of the particles are, and then kind of getting things packaged up, numerically formatted, bundled, and shipped to the next step. Okay, and reduced in volume. So that's what takes it from that raw terabyte per day down to the 100 gigabytes per day. That's all happening in those computer racks. All right. Okay. After that, they take a short trip through geostationary orbit, hop through white sands, which is where the ground station is for that. We shuttle them back here, and they land, in this case, literally in the computers that you see in front of you in this picture. The storage that you're seeing there, so you're seeing 2 computer racks. Those racks are about 7 feet tall. And in there are about 10 petabytes of raw data. And so, with that, we can hold, multiple years of raw data, obviously, but then in addition to the experimental data that we collect, making sense of the data that we get out of the detector requires an awful lot of simulation data as well. Trying to, characterize different aspects of neutrino energies and what things look like in there. That is a lot of work as well. And so, we need a place to put that. So this is one of our storage pools. This is our biggest single storage pool, rolling in at 10 petabytes raw. In order to store things safely, we encode a lot of redundancy information in there. So of that raw data, about 2/3 of it is actually usable. So between 6 and 7 petabytes of the 10 are things that are usable for science data. The rest is redundancy, basically. We have another storage array that is similar in size to this. It's about 75% the size of this one, and that one handles more of the analysis workloads, right? So these things handle a lot of the operational data. So as that detector is continuing to pour data in here, we want to make sure that as people try out their crazy ideas and their analyses, that they're not, stopping us from actually collecting the data that they're going to want to look at. So we kind of separate them out for performance reasons and to keep some of our workloads separated. The analysis storage sees a lot more entertaining sort of work. People have interesting ideas, they write their own code. Hey, let's try this out. And sometimes, it's really easy to make very big mistakes, and actually that's what you're supposed to do, right? If we knew what we were doing the first time, it wouldn't be research, it'd be more like engineering. So, this is going to happen. So we give them a safe place to be able to, do those things, try out their ideas and see what happens. And if it falls over, we stand it back up again and keep going. It's not too bad. All right. But that means we need a lot of computing to sort through all of that. When we get the data, it's not science ready yet. It is in a very primitive form. And so what they need to do are lots of things. There's lots of calibration that needs to be applied. A lot of numerical reformatting. They also kind of package it up in a standard format, and we have software that knows how to read that. And that way you don't have to have everybody basically, developing their own programming just to be able to read and manage the data. So it's kind of the first place where, the common infrastructure starts for our data analyzers. Ideally, we also reduce the volume of data at that point. So that's where we start looking and saying, okay, we do more rigorous analysis on the various events, and a lot of them we just say, okay, these aren't particularly interesting, so they get dropped on the floor. We don't delete the data or anything fun like that, but they're not included in the sort of, higher level data sets. And the objectives that we have, and we generally do pretty well on this, is to be able to say, okay, we can do that sort of processing and turn it around within a day or two of the data, arriving via satellite here in the north. Most of the time we can usually hit that. It takes us, it's about a steady consumption of 600 CPUs or so to be able to sit down and grind through it and produce those higher level data sets. But every now and again we have disruptions, we have facility outages or something like that, or satellite transfers break, and so it piles up at the pole for a little bit longer before it can be transferred across, disruptions like that. But usually in our normal state, we can have it ready within a day or two of collection, at least for the lower priority stuff. So how do we do that? There's a couple candidate architectures. One of them is the kind of the thing that everybody thinks about when they think about heavy duty computing, right? There are big old supercomputers. At one point in time, right after I graduated from UW-Eau Claire, I had the opportunity to work at Cray Research, which produced supercomputers. The machine that you see here is, for my money, one of the coolest computers ever built. That is the mighty Cray 2. It was built in about 1985. At the time, it was a screaming 125 megahertz, which sounds mighty pedestrian, but if you go back to 1985, that was, unprecedented. In that space, it generated so much heat. They were saying between 150 and 200 kilowatts, that they could no longer cool it with air. So the interesting thing about this one is that the circuit boards are actually directly submerged in the coolant fluid in that computer, which is kind of part of the way it looks like it is, because that's actually pretty close to a fish tank. So, but a very cool looking machine, all things considered. Now, the interesting thing about these machines is that they are usually built, or especially at these times, were designed with the intent of getting the most performance you could out of a single program, right? So they were really fast. They had good data transfer capabilities, all of these sorts of things, but they were fiendishly expensive. That machine right there, in 1985 probably ran you somewhere in the neighborhood of about $10 million, $10 to $15 million. So, translate that forward today, and you're talking probably about, an $80 to $100 million computer. That's a little more budget than we have, by a lot, in fact. So we had to do something different. And in fact, what we do is something called high throughput computing. This is a concept invented here at UW in the computer science department by a professor named Marone Livni. I don't know if any of you have ever had the opportunity to hear him talk, but he developed this model when he noticed that there were lots of very expensive workstations sitting on people's desks that were idle a good chunk of the day when they weren't working on them. And so he got the idea at some point about saying, hey, what if we could run programs on those while their owners were away? And over time, that morphed into a much broader scope. So in this model, it's not so much about saying we're going to run a single program as fast as we can. It's about saying how many programs can we possibly run at the same time, okay? Now, each of those systems has their weaknesses and strengths. The trick is that not all problems can be solved by breaking them up into tiny pieces and running as many of them as you can, right? Some of them are, have lots of interactions. So weather prediction, for example, and, atmospheric science, changes in one part of the atmosphere propagate through other parts of the atmosphere. So you can't just divide your atmosphere into cubes and compute temperatures and pressures and humidities and things within that cube. As soon as you do that, and as it changes through time, those effects push through the entire domain. And so you need to use very different programming techniques to be able to deal with that. So for those, kind of some of the traditional supercomputers that have mechanisms for dealing with that sort of problem are preferred, generally speaking. But for us, we're lucky. For our data, our analyzers are usually interested in individual events, and they are discrete. They don't interact at all. So essentially, we can divide our data up into as many pieces as we want, and every CPU we can find, we can use them all and keep them all busy. Back in the day, this was called embarrassingly parallel. We prefer the term pleasingly parallel. This is great. It works for us, and so it makes the programming problems much simpler. Going through that. All righty. Cool. So that translates then into our local computing cluster. Now, this is just the cluster that we've purchased for handling, or built out, I should say, for handling IceCube computing job. For us, you can see some of the vital stats there. This is by no means huge, right? I mean, some of these numbers, depending if you haven't seen these things before, may look sizable, and in some ways it is. But there are many clusters around the world that are much larger than this, and in fact, there's probably half a dozen of them floating around the UW campus that are at least this size. But it gives you a rough idea of the scope of computing that it takes to deal with this data set, right? Because we do have to comb through, at a minimum, 100 gigabytes a day worth of that data and do the interesting feature extraction in there. And that is, a healthy workload. Okay. All right. But yeah, that's not enough either. So, as I say, UW campus has multiple resources of about this size. Lots of the people, everybody is willing to share when they are not keeping their resources busy. We try to share amongst each other to get the most bang for our computing dollar. Nobody's budgets are infinite, it turns out, and so the more we can kind of share and work together, the better off we'll be. But even that isn't enough, and so we farm out work to our collaborating institutions. We farm out work to other universities. So, we saw the grid computing in there, and really what that means is, universities and government labs who have, facilities similar to ours who are willing to make those available. All of these, for the most, are kind of share and share alike. So there's very few where there are any pay for, real hard money for an allocation of time on these or for using them. It's if they're available, go ahead and use it. And supercomputer centers, right? So we don't use supercomputers. Well, we can. Our programs will run there. And we do make use of them on occasion. The tricky part is that they are very different looking computers, both in terms of the way they're built, but also in terms of their network access. So frequently supercomputers are considered national level resources. So security concerns are very high. Some of these are in Department of Energy labs, where they have classified and unclassified research going on, so they're very, very attentive to security. And so sometimes the data flow that we'd like of just being able to move things kind of back and forth doesn't work the same way. So we have to put in software to kind of handle the staging in and staging out of our data into those facilities. So they're a little trickier to use. You get a lot of power, but at the same time you pay for it in the effort to use them. And of course, nothing would be complete these days without the cloud. We do make occasional use of it. We're working on using it more. One of the interesting applications as they sit down and we get that alert coming from the pole is that we say, okay, wait a minute, at the moment we drop everything. And on the compute farm that we had there, we sit down and we start grinding on that. So we're trying to do the most accurate reconstruction as we can. And then we're looking at sky maps to see if there's anything interesting in those areas and, doing a lot of that analysis. And that might run for 3 or 4 hours, consuming all of the compute resources. As you might imagine, the other researchers who are using the computer at the time are unhappy about that. So one of the things we're looking at then is shoving that workload off into the cloud, because that's kind of an ideal use for that. We get, maybe 2 or 3 of those sorts of events per month, and an hour or 2 of computing time at that scale, runs you a few $100s. So it's not a bank breaker by any means. So that's work that we're looking and taking from early stage development, kind of that initial proof of concept, and then saying, okay, let's translate that into the cloud. Not only that, a couple of years ago, we did a big experiment collaborating with UCSD. It was really kind of almost more of a publicity stunt at the time at some level. But the idea was they were going out and some of the folks at UCSD were looking and talking to the big cloud providers and saying, how many GPUs do you have, and how many can we get? And oh, you can have as many as you want, and we have tons and tons, and how many? And when you started asking questions about actually using them, the numbers got really waffly, right? Well, maybe we have this and we don't know. So they did what any good experimental scientist does. And they said, hey, they went to the NSF and said, we think we need some money. We're going to measure it. And so they went and they asked the NSF for money and said, we want to buy all the GPUs we can from Google, Amazon, and Azure. So the 3 big cloud providers, we want to buy all of them. Okay. And so they worked, did some work with the teams at the cloud providers to say, okay, can we work that out? What can we do? But then they needed a workload, right? I mean, it's one thing to say, okay, can you get the GPUs? It's another thing, can you make it useful? And they did want to be able to say, hey, it's not purely a publicity stunt. We want to actually produce a usable data set. And that's where we came in, because we can, given the nature of our data, being able to chunk it up into arbitrarily large amounts, we can actually use that sort of model. So they did that. They basically went out and bought all the GPUs that the 3 cloud providers would sell us for about 2 hours. That turned out to max out somewhere right around 51,000. I think it was like 51,500 or something. So for 2 hours, we were able to basically use all of that compute power. It produced the data set. That was great. That was about 5% of what we think we would need in a year. The cost for that, they're fuzzy on the numbers and they don't want us to talk about them in too much, but it was north of, probably north of 120,000. So, if you sit down and you multiply that out, the numbers get pretty breathtaking pretty quickly. But as a proof of concept, it was the largest scale experiment of its type to be run at that time. I think it's been superseded by now. But that's the kind of computing resource we are capable of using, and in some cases they would love to use it. We just can't afford it. So that's great. We have all of these wonderful machines all over the place, but how do we glue them together? That is no small feat. And to do that, we use a beast called HT Condor, which was what Marone Livni invented here at UW. That takes care of making sure that as programs get run on different computers, that if something fails with that particular computer, it crashes, or there's an error of some type, or even the program itself crashes, it will just say, okay, well, we'll try it again over here, and just keep trying and trying, and managing all of that. And hey, wait a minute, this program needs this data. Okay, shuffle it over there, and doing a lot of the heavy lifting behind the scenes to make that happen. It also requires lots of databases and fun things like that to track all of this, because Condor does the mechanics behind the scenes, but it doesn't know what our data is. So it really can't tell us, yes, you've completely finished processing this data set. It can just tell you, I've made sure everything I know about has run. So we still have to do a lot of the bookkeeping work there. And yeah, fast networks, because data is moving. That's the one kind of downfall, if you will, of some of the throughput model sorts of things, is that it involves a lot of data moving back and forth. It doesn't just sit on one machine and get, you know, ground through very quickly. So we consume a lot of network traffic. All right, mission accomplished now? No, okay, kind of. Our analyzers are analyzing and they're running around and they're happy, so that's great. But this spring, coming up in a few months here, a pile of cargo is going to arrive on our loading dock. And we're going to have to get that replicated and archived off of there. And so that's kind of an ongoing development effort for us at the moment. We've done that, but a lot of it has been manual processes over the years. So now we're really working on the, okay, you know, let's get this stuff, you know, automatically packaged up, moved along. You know, let's index it. Let's make sure we can track it appropriately and properly. It's an interesting area because, you know, traditionally for a lot of these data sets, you know, I've been around the university for a long time. The way scientists normally deal with data management and archive is they, you know, they copy it off onto, it used to be tapes, now it's USB hard drives that they got from Best Buy, and they put it on their desk. You know, and that works. But when you start getting to these big data sets, right, by now we're looking at 10 years of lifetime on these. So, you know, from that standpoint, you're looking at multiple petabytes of data. That's a big pile of hard drives, and it's really, really slow. So, you know, those don't work anymore. Those tools don't work. So, you know, now we have to do the heavy lifting of saying, okay, let's do it properly, index it, and automate that whole thing. And so that's really kind of the, you know, the process. It does ultimately, ironically enough, end up getting written to tape on the other end. You know, and so that's why we do these things at NERSC and at Daisy Zeuthen, which is one of our collaborators over in Europe, is that they are, you know, major government labs, and so they operate a tape robot. We used to run one here at UW, but they are expensive to run. One, you know, a sizable one runs you about $200,000, and it takes a, you know, a fairly sophisticated technician to be able to, you know, to manage the thing. So at some point we said, okay, wait a minute, we have collaborators in these other areas, and they can use that as kind of an in-kind contribution for participating in the IceCube collaboration. If they're willing to archive the data, then, you know, then that's part of their contribution.
Steve, is it really zip compression?
It is.
Oh my God. Okay. That's just very funny.
Well, so part of what happens, the tricky part, there's a lot of different ways you can kind of bundle up the data, but one of the things you want to be able to do, the nice thing about zip, and the reason they're using that at the moment, is that it's very quick to inspect the contents of the file, of the compressed bundle of files, to kind of basically get the table of contents for that. Other things that we've looked at, yeah, you can get it, but it takes a long time to generate that. And so this is very quick that way. So, but
Thanks.
yes, it really is, you know, honest to God, a lot of these things, it's the same stuff you use every day. It's just, we do it a lot more, you know, nothing fancy.
Hey, Steve, this is Kevin Santos. I was just wondering if, when you're talking about that, the stuff you use every day, have you had, is everything proprietary software here in terms of the analytics? Or are you using anything like IBM for predictive analytics or anything like that? Or have they shown interest in it, or is everything proprietary?
It's all internally developed. You know, it's so, and kind of proprietary. You know, they are working, you know, different parts of the packages are released. So parts of it are, you know, public domain, but other parts of it are internally written software. At the moment, we're not using really kind of any off-the-shelf commercial software for any of
Like
those.
like Python or anything like that?
So we do a lot of the, yeah, a lot of the programs, a lot of the scripting is in Python.
Okay.
Chunks of the low-level processing are C++ in some cases.
Gotcha.
But these days it's kind of getting to the point, depending on what you're doing, that, unless you really, really need the performance of C++, you just stick with Python.
Gotcha. Thank you.
Yeah, no, thank you. That's a great question.
The processing that you do, are you Linux based or what are you based?
Yeah, we're predominantly Linux based. Yes. So all the computing infrastructure and all the heavy lifting there is Linux on all of these. Our and use the stuff we sit down and key bang on day to day. We have a mix of things. A lot of our scientists use Mac for their desktops and things like that. There's a small chunk of Windows and a little bit of Linux on the desktop as well. That's mostly for the coding gearheads on the Linux side. But yeah, that's the heavy lifting processing itself is all Linux based.
Steve, a little bit past the half past the hour here.
Yep.
I don't know if you've got any more presentation you want to do, or if you just want to transition and just open up the floor to questions now. But
very little. I'll flip a slide here because this is kind of the challenges. So we can come back to this in just a little bit if people want to ask questions about that stuff. My thanks and credits. So thanks again to all of you for enduring this. Hopefully it was not something you were using to prepare for a good night's sleep. And most of all, this is the fam. They had to deal with this. So this is 2013. Those kids right now are 14 and 17. My wife is a saint. I left her alone. That was the second trip to the pole. The first one was in 2009. So I left her with a 5-year-old and a 3-year-old for a month and a half. And she did not throw me out. So.
Cool. Thank you,
go.
Steve.
Yep. No, thank you all. It's been the time has flown.
And we've got a little time left. So if anybody else has any questions, feel free to unmute.
Steve, I do have a question. The data flow, the types of information you have in general mirror what some other large scientific collaborations like the LHC have. Is there any sharing at all of technology or processes between these large collaborations, or would that only happen, say, at scientific conferences?
There's a degree of sharing. Now, some of the data are similar, but they're only similar. So, at the analysis levels, I mean, that's all still pretty particular to the instruments and the science you're trying to do. But a lot of when we talk about the grid infrastructure flowing around, okay, as we move our processing to different institutions around the country and around the world, a lot of that is riding on the back of the LHC. For them, if we sat down and said, hey, we triple or quadruple our computing budget, we could probably do all of the computing for this thing, locally on campus. LHC simply doesn't have that option. And so, they have a huge amount of infrastructure to be able to move their data around. It's breathtaking when you look at some of the things they talk about. But we leverage all of that. Okay, so a lot of the communications protocols and a lot of the getting jobs fired up and scheduled, programs running in other locations is leveraging their work extremely extensively.
Yes. Can you hear me?
Yes, yes.
Yes. What has been discovered from all of this? What scientific discoveries?
Oh, yes. Okay, well, so this is where I fall back to me being the computing guy. No, but there are a few kind of big things that happened. So early on, there was a sort of undercurrent of concern, because the idea behind the detector was to say, hey, we want to detect these astrophysical neutrinos, but that was kind of a leap of faith, because we could look at the physics and the models behind them and say these should exist, right? But it wouldn't be the first time we thought something should exist, and we find out that the universe fails to cooperate. So early on, we weren't seeing a lot. And it was like, okay, well, we can set limits on some of these models, right? So, oh, well, you know, obviously then supernovas can't be producing neutrinos at these energies. And, you know, so these models are now excluded. They're no longer good. And that's important scientifically, but that's, you know, for the researchers in the group, you don't really wake up in the morning thinking, gee, I'm going to set a limit. You know, you're really looking to see if you can, you know, discover something new. So I think it was about 2015, they detected one of the first things that they could pretty definitively say, this is an astrophysical neutrino. So everything they'd seen before that, you know, they couldn't say it was astrophysical, maybe, but, you know, it could have easily been ones produced by particle interactions in the atmosphere, you know, or solar neutrinos coming from the sun. So in 2015 or so, it was just pure luck. A lot of the analyses they do when they're looking at the data, it's blinded. So they sit down and they write their algorithms against a smaller subset of data that they call the burn sample, so that they can use that to develop their code and, you know, and look at their analysis, but they don't get to look at the real data until they've actually, you know, gone through that process. And part of that is just to keep people from, you know, kind of cheating a little bit and tuning their algorithms to find what they think should be there. So they blind the big stuff. But, you know, you need to be able to write the code as well. So, you know, in the burn sample, so this is 1% of the data, and it's just comes in raw and people can look at that and work at it. They actually found one of these events. And basically, you know, when they saw that, they were like, what the heck is this? Because it was like, you know, they'd never seen this before, or they didn't know they'd seen it before, I guess. And so they started looking at this, and really the energy level for the neutrinos. So this is where the size of the detector comes into play, because in order to accurately calculate the energy of the neutrino, you have to be pretty confident that you captured all of the light that it produced, right? And so, you know, smaller detectors, you know, if you saturate the full detector, you don't know how much got away. So when they're looking at some of these events, they say, hey, wait a minute, here's all the light that came from this. And as long as we have no detections on the 2 rows of strings along the outside, and then the 2, you know, or the 2 columns of strings along the outside and the 2 rows up on the top and the bottom, then we know it was contained and we know we got all the light. So they saw an extremely energetic event, you know, that they could say, hey, wait a minute, here it is. And it simply was not possible, you know, physically possible as far as they understand physics, that, you know, the sun or anything local could produce a neutrino with that level of energy. And so that kind of validated the design of the instrument. And there, you know, there have been lots of other interesting things that they found out in the particle physics world. And, you know, I could try to wing it here, but I would probably wildly mislead us, you know, or send us down a few blind alleys. But one of the other things that they did find, you know, in the MMA world is, and this was 2 or 3 years ago, they actually caught a particle, and they weren't sure at the time, but they're becoming more sure that it was actually part of an active galactic nuclei, so a blazar. And they happened to catch it right as it was flaring. And then another, I think the Fermi detector also happened to be, you know, catch part of this in their data set as well. And so there's a few different things, you know, so this is kind of stitching together some of these instruments to say, hey, you know, are we seeing, you know, similar things with that? And part of the trick is that when you're reconstructing the track, one of the big variables is understanding the ice surrounding the detector, because it is very clear, but it turns out it's not without structure. And that's what a lot of what we use the GPUs for, is simulating propagation of light through the ice. And so they compare their simulations with what they actually see in the detector. And then they keep refining that ice model, they call it, right? So what does that ice look like? How does light travel? It turns out that the water, the ice immediately around the detectors is still very cloudy, right? Because they drilled, you know, basically drilled a column of hot water in there. So now you have lots of, you know, dissolved gases and things in there. So as that refroze around the detectors, not all of those bubbles got out. So there's a little bit of cloudiness around those. So yeah, and that affects how the light travels through there. And, you know, given the analyses they're doing, it turns out that can also have an effect on the track itself. So they have to be able to correct for that to make the track accurate. And so, but so that's why I say they're, they're pretty confident at this point, but they're, they're always hesitant to say 100%, but they're fairly confident that yes, they did actually see this and it actually came from that blazer. So those are kind of the big things, scientifically speaking.
Steve, if I remember,
Okay.
each of the DOMs, each of the modules can actually emit light, and that's how they do the calibration, right? That's how they characterize the ice, is they have them fire off light of a known value, and then they can measure the propagation.
Yep. Yeah, there are LEDs on each of the DOMs. Yep.
Steve, when you're, I'm thinking back to that grid of hits that you were getting with the neutrinos and other data that's irrelevant.
Yep.
How much of your algorithms right now can actually learn to eliminate some of that, some of the trash? And I know you said in your last slide here that AI and ML is coming.
Yep.
Is that going to be proprietary too, or are you looking at other companies to help you with that?
It's probably going to be it's a good question. I'm sure it's going to be a mix of things. So, some of the early stuff we'll be looking at and just trying to understand, how this stuff works, because this is active research at the moment for us. So, we've had people looking at some of these techniques for a while. There's a couple of interesting things. So one part is looking and saying, can we train it to be better at filtering online at the pole, right? That has a tremendous amount of value. But then there's a question when we look at the deeper, hey, we're going to use AI and ML for these. And when you talk about doing science with that, the question is, okay, we can maybe teach the AI and ML to identify things, to see new and interesting things. But if we don't understand why it did it, are we really doing science, or is it just another black box?
Right.
So, at the moment now, I think this will be a shifting thing. It's really, a new area in many ways.
Yeah, there's always seems to be a danger when you try to put in too many restraints into an algorithm that you start eliminating data that you think is useless, but it ends up not being useless. Yeah.
Yep. Yeah, and that's the trick. And that's why at some level we don't actually discard any of the data. And these were discussions early on, right? So, originally when the detector was being built, hey, this wasn't going to be a big data volume because, the only stuff we're interested in is this very high energy stuff. And so anything that doesn't meet a certain energy threshold just goes away. And all of the low energy people were like, but that's my science, right? And so, many spirited discussions ensued. I was lucky, I'm a computing guy, so I'm just like with the popcorn, just like, you guys, you go. And it turned out that being good scientists, this is a universal truth I have found with scientists, all very different depending on the domain. I have yet to find one who's like, yeah, just toss that data. Never seen it, ever. In 25 years, I've never seen one willing to do that. And, and for good reason, because as you say, the possibility of losing something, and in some cases you can say, hey, okay, maybe you can run the experiment again and you don't have to, keep this. But in cases where you're doing observational stuff like this, the universe doesn't give you a replay. So.
Yeah, you never know when some other observatory or some other instrument is going to they're going to find some interesting event that happened a couple of years ago, and then people are going to want to go back and look at your data and look for a confirmation. So
there's a big example.
Excuse me.
Go ahead, Win.
I was going to say, this isn't so much a question, but you might be interested in the story. I worked for a number of years at a company that was originally called, when I joined at Bjorkston, Bit7, that was involved in the IceCube project in terms of project management and also writing some of the technical specifications for the detectors. My tenure briefly overlapped with an electrical engineer who was involved with the installation of the equipment down at the South Pole for a number of seasons. And he told us a number of interesting things about the South Pole that most people don't think of, like the fact that some people can't adapt to the altitude because the South Pole is actually a very high plateau. And also the air is so ultra dry that you have to be extremely careful about static electricity when you're working with the electronics down there. But at one point we asked him, well, how did you get recruited for this project? And he said, oh, I answered an ad, and it said, basically it said, wanted engineer to work at a remote location. whereupon one of the people said, well, I guess there's nothing more remote than the International Space Station. And I said, no, if you stop and think about it distance-wise, the space station's harder to get to. It's actually a hell of a lot closer than the South Pole.
It is not easy to get to the South Pole, especially by boat.
No, there's a whole process that he described going through and going to New Zealand and getting outfitted and waiting for the right time to fly down and all that, and the rigors of actually doing all that stuff. So, and then that's in the summer. In the winter, it's even harder for the people that have to stay down there. But it definitely was very interesting to talk with him about his experiences.
Steve, I do have two questions here. Two questions that are actually separate. But first of all, in terms of archiving data and keeping it around, I found that the virtue of doing that was, do you remember the story of Voyager and the anomalous acceleration around Jupiter? And they had to go back and find all sorts of data that were, or was a Pioneer, I forget which, but it was all sorts of data tapes that they had to go back, and they found data tapes in somebody's garage that they had to use to find out. It turns out it was all heat related, but who cares? But the questions I had were, I know that there are at least 2 other neutrino detectors being built, one I think in the Mediterranean and one somewhere else. Is there any coordination between these at all? And the second question is, if I can remember what it was, expanding the detector. Right now you're between 1.5 and 2.5 kilometers deep, which means you're kind of on bedrock. So if you expand it, you have to go laterally, is that correct? And what are the plans for that, and what's the time frame for it?
Indeed. Okay, so first question, as far as other neutrino detectors, yes. So I think Antares is one, for example, is probably one of the ones you're thinking of, and absolutely, these things, now some parts of it, it depends on coordination, but usually at least data sharing, different things, looking at this and saying, okay, what are you seeing? They definitely are, at the very least, talking with each other. I don't know that they're necessarily sharing code across these or, any of the tighter collaboration, but, those are the sorts of things also that sometimes come over time. So I'd expect for some of these, as they start operating more and more, you'll start seeing more of a fusion of those, if I had to guess. So the next question, the big one, expanding, yes, you have to go laterally. So they're looking at a very different scale. I think they're trying to get that out now in the lateral dimension. So at the moment you can kind of look and, it's not quite a cube, but it is close to a 1 kilometer by 1 kilometer by 1 kilometer layout of PMTs. And they're looking at expanding that laterally, I think out as far as 10 kilometers if they can. And some of these will be spaced further apart because the ice is clear. So at first they weren't sure exactly how clear the ice was, what it was going to look like. So they put the strings close, as far apart as they thought they could without losing any sensitivity. And now they know that they can space them out much further. That light propagates very well through the ice. And so they're looking at expanding it that way. But in addition, they are also looking at, you can also use radio detection for neutrinos, and that has the advantage of not having to be as deep. It's because you're not doing these things optically, so you don't have to necessarily be worried about light contamination and fun things like that. It has the disadvantage of being kind of noisy because, well, it's working in radio. And so, you know, I know some of the early prototypes they've had, you know, interference from the plane engines, they can pick up as they're coming and going. So the background reduction becomes much harder for that experiment. But, you know, that's what they're kind of trying to do if they can. The time frame for that, ideally, there was, they were looking at an upgrade to the current detector. And so that was basically going to be an R&D effort surrounding newer photomultiplier tubes and newer geometries of those, and put them in the existing volume of the IceCube detector. And that was just to get our feet wet and get us used to drilling again, because that's a whole different world. But then the bigger expansion, what they're calling Gen 2, Generation 2, that was slated to start kind of in 2025-ish. But COVID has really pushed plans back like crazy. And for a project of that scale, I mean, they're ballparking that somewhere, you know, north of $500 million. And at that point, that turns into a congressional level approval. That's a committee meeting, basically. So.
Well, thank you so much, Steve, for your presentation and answering all the questions. And, you know, it seems more and more often, I think just a few months ago, where if you watch programs like NOVA, you get to see all the research that's going into neutrinos detection, and none of them give you a real taste of all the programming and processing and engineering challenges there are to be able to discover all this new information. So thank you so much for presenting to us tonight. And there's a lot of really deep food for thought and understanding on this topic in this great instrument we have, IceCube. So thanks again, Steve.
Oh,
Thanks,
thank you
Steve.
guys. Thanks for having me. It's been a pleasure.
Thank you.
It was great to meet you all.
Yeah, thank you. This is
Me
great.
too.
Thank you, Steve.
So
Thank you, Steve.
Good
that
night.
will conclude this month's meeting of the Madison Astronomical Society, and join us again on Friday, February 11th.